Hi, I'm Kevin Murray, owner and CTO of Overlab. The topic of this tech talk is augmented reality maintenance with equipment state recognition. We are developing fully automatic equipment state recognition so that augmented reality solutions can use that information to provide relevant and precise holographic instructions to equipment maintainers. A common analogy is GPS navigation. This provides clear step-by-step instructions from your current state and perspective. We want to do that for equipment maintainers. Clear step-by-step holographic instructions that tell them what to do and where from their perspective. And in order to do that, we need to recognize the state of the equipment. First, a little about Overlab. We are a small business that was created specifically to provide computer vision solutions to the DoD. So we have technical expertise in computer vision, machine learning, and I would say, arguably, most importantly, synthetic data. While we are a small business, we are also supported by a network of expert consultants and subcontractors. So we really prefer to bring in subject matter experts to the projects that we do as needed, rather than trying to grow Overlab to fit projects that go beyond our expertise. And we are based in Northern Virginia, so we're easily accessible to many Navy and DoD facilities. So here's the Navy challenge. Equipment maintenance is an enormous effort for the Navy and the DoD in general. You can see some statistics here about the number of workers required to maintain the fleet and their levels of experience. So in order to increase efficiency and reduce downtime, the Navy has been pursuing augmented reality to guide maintenance workers. I think the image here really conveys that intuitive GPS navigation type interface where holograms instruct the maintenance worker on what to do and where from their perspective. In addition, the Navy has very specific requirements that are different from the commercial side of things. Specifically, they need to operate without physical markers, such as QR codes being placed on the equipment. They need to operate without networking or cloud services, and they need to be able to operate both indoors and outdoors in bright sunlight, which is a significant challenge. Existing solutions do not meet those Navy requirements. Additionally, they're limited to completely rigid equipment with no missing parts. These are severely limiting restrictions in equipment maintenance, and we show two examples here of why that is. If you look at the top right, we show this robotic arm. You can imagine that this robotic arm can move around, and it can exist in various kinematic states when those joints in the robotic arm change their angles. We cannot place holograms if we do not know what kinematic state that robotic arm is in. So recognizing the current kinematic state is a fundamental requirement for guiding maintenance workers on objects like this. So that is one of the things that we're looking to solve. At the bottom right, we show an image of an exploded assembly. Assemblies, of course, real equipment is represented as assemblies. It's not just one part. It's dozens or even hundreds of individual parts that are put together. And you can imagine that dealing with assemblies, removing and adding individual parts, replacing parts, is a very fundamental maintenance activity. So we want to explicitly deal with that. And so we deal with that by recognizing that that's what that equipment is. It's individual parts that are placed together at specific positions and orientations. So we want to recognize both where that equipment is, even though it may be missing parts, and we also want to recognize which parts are present and which are absent, because then the system can use that information to actually guide the user on the next step in the assembly or disassembly process. This is why we call the problem equipment state recognition. We recognize that we're not simply localizing equipment relative to the user, but also recognizing the current state of the equipment. So our core capabilities include pose estimation, but also the more advanced capabilities like assembly recognition and kinematic or articulation recognition. We perform that recognition with two key pieces of data. First, we assume we have a CAD model of the equipment. This CAD model describes the geometry of the equipment, potentially including that assembly or kinematic information. And we use this to automatically generate high-fidelity synthetic data, which can be used to train our neural networks. So given a CAD model of the equipment, we can automatically obtain a neural network that is able to recognize that equipment in the field. And then in the field, we run that neural network against visible light images obtained from a camera on the AR headset as the user observes the actual equipment. The usage of visible light for this purpose is somewhat unusual, given that most AR headsets can actually provide spatial data of the environment. And that spatial data is a natural modality for our problem, but it fails in several important use cases. The reason it fails is because that spatial data comes from a time-of-flight based depth camera. And that active sensor just gets completely overpowered by sunlight when you're outdoors in bright sunlight. Additionally, indoors, it can present a problem for certain surfaces of equipment. So for dark surfaces or shiny surfaces, that emitted infrared signal can either get absorbed by the equipment or reflected in a random direction, preventing a return and preventing the measurement of that distance. So there's several important use cases where the time-of-flight based depth camera simply does not work. And we want to support as many use cases as possible. So for that reason, we use visible light. And visible light cameras do work in all of these cases. However, there is a major challenge in matching visible light features to the equipment because we do not assume that we have color or material information about equipment surfaces. This is because the CAD models do not generally provide that information. They typically just provide geometric information, and we want to work with as many existing equipment as possible. Additionally, later on in the field, that equipment could be painted or fixed with instructions and warning labels that change its surface appearance. So we believe in general, we cannot rely on knowing the surface properties of the equipment in advance. So here's our current status. On the left, you can see some results for rigid body pose estimation. In these images, we've rendered the object model according to the pose that we estimate. So that's what that green outline is showing is the mesh of the object rendered to that position and orientation that we estimate for that given image. And you can see in these examples that we're dealing with objects that can have dark or shiny surfaces. Additionally, we're working in environments with bright sunlight. So you can see in the top two images that we're dealing with strong shadows that are cast onto these objects. Now, at the time of this recording, this slide is about 6 months old. So in these examples, we're estimating pose just from a single image. And with just one image, our pose estimates are successful maybe about half the time. But as we hypothesized in this slide here, we can indeed dramatically increase our success rate by just processing multiple images. And we can easily do that with typical commercial augmented reality headsets because they have video cameras, typically at around 30 hertz on them. On the right, we show some initial results for assembly recognition. While much of our testing is focused on synthetic data for this problem, we have been testing on an actual 133-part Briggs & Stratton engine. In preliminary multi-view testing in this case, we were able to estimate not just the pose of this engine, but also the presence of each of those 133 parts, in this case to about 90% accuracy. So definitely some promising initial results for this advanced capability. Here we show our projected technology readiness levels, or TRLs. In general, we're focused on making the solutions work robustly before we try to make a prototype near the desired size and weight. And that's especially true for our advanced capabilities of assembly recognition and kinematic state estimation. But we're expecting all of these capabilities to be at TRL 6 or 7 by the end of the phase 2 option. So that will be sometime in the summer of 2024. So to summarize, we're providing a solution that meets the Navy requirements of cybersecurity, avoiding physical markers, and working in challenging environments. Our focus on visible light cameras allows us to work both indoors and outdoors in sunlight, and also allows us to work with equipment that has dark or shiny surfaces, which we view as being a common situation. Additionally, we're addressing the more challenging problems of assembly recognition and kinematic state estimation, which we view as key enablers of augmented reality equipment maintenance. So looking ahead, our primary goal is transition to the fleet. So we need access to Navy facilities to perform the operational testing, and we need funding to take us from TRL 6 or 7 to an actual commercial product. We're also really interested in expanding our capability. Again, we view this problem very broadly. We want to estimate equipment state using live imagery and pre-existing data about the equipment. So that equipment state could include things like fault detection and diagnostics, and the pre-existing equipment data may go beyond just simple CAD models. So we're really excited about potential future problems that we can solve. We've identified two main transition points for this technology: PMA 260 for aiding actual equipment maintenance activities, and PMA 205 for training equipment maintainers. And of course, we're interested in some broader applications that our technology can support. I mentioned extensions like equipment diagnostics, but there are also potential tangents such as synthetic data in general. Synthetic data is something that we are very excited about. It has been extremely useful for us, and we're very interested in helping others make great use of that. Thank you very much for taking the time to learn about our company and our technology. We're very eager to work with others in similar areas, so please do not hesitate to reach out to us. You can see our contact information here. Thank you again.